Okay, so this week is all about work and relating that to force and relating that to energy. And so I'm going to do one activity as a pre-video that connects the work done by gravity and also its energy. So the point of this entire activity will get to the claim that the work done by gravity is equal to the minus change in potential, the gravitational potential. And so I'll just go through this so you believe that this is true. And you can just remember that the result is really the most important part of this. So first, we write the dot product of F dot delta r, the displacement vector of the object that force is pushing on, in component form. So F dot delta r is going to equal the x components times each other, f sub x times delta x plus f sub y times delta y. Okay, first step, easy. Okay, now choose the conventional axes, so that's y up and x to the right here, and find an expression for the work done by gravity on an object of mass m. And so remember that the force of gravity is equal to, in component form, 0 and minus mg. So now the work done by gravity is F dot dr, so the work done is this in component form, but now this is our F sub x, and this is our F sub y. So F sub x is 0, so this is going to be 0, and then we have F sub y, so this is a dot product, right? So it's plus F sub y, which is minus mg times delta y. So I'm just plugging in F sub y. That's the only thing we're doing there. Okay, so then we could simplify this and write minus mg delta y. Okay, so now we want to know what's the relationship between the work done by gravity and the change in the gravitational potential. So basically, I want to get to this up here. So if you remember, the change in the gravitational potential is U final minus U initial, which is equal to mg, the final height, minus the initial height, and this is mg delta h, or in our coordinate system, that's mg delta y. Well, we can plug this in right here and rewrite this equation as the work done by gravity is equal to minus delta u gravity. So basically I just took this equivalence, the delta u sub g is equal to mg delta y, plugged it in right there. And so we get this claim that I said we'd get pretty easily. Okay, so let's look at a particular example and make sure that this is true there. So if we consider a block that's going down an inclined plane and we have a different set of coordinates, will this still hold true now that we have a different coordinate system? Well, let's look at delta u, gravity, and let's look at the work from gravity and see if they are in fact negatives of each other with the same magnitude. So if you have this block that's going down, so it's starting up here and then it goes down here, so it's going about this height downward, which is, if we look at the angles here, this height that it's fallen vertically is going to be L cosine of theta. Okay, so what that means is we can write this as our mg delta h, and then remember this is mg h final, which is a lower point, minus h initial, which is our higher point. It's higher by L cosine theta, so this is going to be mg, right? So the the initial one is negative, right? So the h final is the one that we're going to say our reference height is here. So then we have this is going to be minus this L cosine theta. And so hopefully if we calculate the work, we'll get the same thing without that negative sign. So first, let's look at the force of gravity, that vector, in this coordinate system. So here we'll have mg, but the x and y components, instead of being just mg in the y direction and 0 in the x direction, what you'll find if you just break it up, you'll find that you get cosine theta and minus sine theta. And then the delta r is just going to be in the x direction L. So our F from gravity dot delta r is equal to mg cosine theta minus sine theta, and then dotted into our displacement vector, which is going to be 0 in the y direction, and then it's going to just be L in our x direction, and then just multiply this out, and what you'll find is you get mg cosine theta times L, which, if you look at this first line up here, is equal to minus delta UG. So I'll let you think about the bonus, but the point here is just that this equation holds true whenever you have gravity, and we'll find also for other conservative forces like the force from a spring. I hope that helps.